In this lecture, we are going to talk about demodulation of angle modulated signals. For demodulating frequency modulated signals, what do we need? We need a system or device whose we need a system or device whose output is sensitive to the angle of the incoming signal or phase of the incoming signal. That is what we are looking for. Okay, so the input is FM signal or PM signal, and the output is sensitive to frequency of the incoming signal or phase of the incoming signal. So let us first talk about frequency demodulation. Frequency modulation, demodulation, FM demodulation. Basically, it requires a circuit which gives an output proportional to the frequency deviation of the input, right? After all, where is the information residing in an FM signal? In an FM signal, the information is residing in the frequency deviation delta F. Okay, as the instantaneous input frequency varies, you like the output of the device or circuit is vary accordingly, right? So devices or circuits which can do this job are called discriminators. So generally in FM demodulation we call discriminators. So sometimes we call demodulator and sometimes we call discriminators. More precisely, they are called frequency discriminators. Because they are able to discriminate the frequency of the incoming signal. Okay, now let us see this mathematically. Suppose you receive the modulated signal. Let's call it x suffix r of t, and here this r denotes the received signal. R denotes the received signal. R means received. Okay, now let me write down the received signal x suffix r of t is equal to AC cos of omega ct plus phi of t. Then you need an output from the discriminator. The discriminator output, let me call y suffix d of t. Here d denotes discriminator, output of the discriminator. And this output of the discriminator should be proportional to d phi of by dt. Okay, why is it d phi of by dt? Because in the input your phi of t is nothing but, if you recall, phi of t is equal to 2 pi kf integral of m of tau d tau. Okay, so what is your m of t now? M of t is let me put a proportional to derivative of your d phi of t divided by dt. Forget about the constants. Okay, therefore your y d of t is proportional to d phi of t divided by dt. So let me put the proportionality constant here, that is k suffix d, then d phi of t divided by dt, because the frequency deviation is proportional to phi of t, instantaneous phase. So ideal discriminator output should be having an input and output characteristics like this. So this is the relation between input and output. So you can see for an FM signal, phi of t can be written like this: phi of t is equal to 2 pi kf m of s times ds. Okay, so now you can substitute here this phi of t. So k suffix d times d by dt of, what is your phi of t? 2 pi kf, then integral of minus infinity to t m of tau d tau. So now kd is constant and kf is constant, 2 pi times d by dt of the integral of this thing, that becomes m of t. So let me put some constant. This is, I will observe in this one, it is, let me write down, this is kf dash, then this also kf dash, let me call this kf times 2 pi, this is 2 pi times kf dash is equal to kf. So the whole thing is kf. So kd times kf times m of t. So this is my discriminator output. Okay, so this is, okay, this is what you want, okay, that is, you want output proportional to message signal. You want to get your message signal back after demodulation. What is kf here? Kf is FM generator constant. Generator constant, or the modulator sensitivity factor that we already discussed. And this kd is, k suffix d is FM discriminator constant. So if you want to express this factor graphically on the graphically, this guy in this relationship, on the x-axis, suppose I show the input frequency, okay, and then what kind of characteristics do we want? When the input frequency is equal to the carrier frequency itself, that means what? At that instance, the message signal value is 0, right? If you take your modulated signal, x of t is equal to a times cos of omega ct plus phi of t. When will the frequency will be, the instantaneous frequency will be fc? The whole thing is fi. Now we are asking the question, at what condition you will get a fi equal to fc? When phi of t equal to 0. Phi of t equals to 0 means what? M of t is 0. If there is no message signal, then what output should I get? I get 0 output. This is my output. So when the frequency is fc, I should get a 0 output. When the frequency increases in the forward direction, then my output also should increase linearly. When the frequency decreases, then my output also should decrease. Therefore, I will get a straight line curve. With a certain slope, of course, straight line. So at the carrier frequency fc, the output should be 0. Okay, here I am plotting the output voltage versus input frequency characteristics that you would like to have in a frequency discriminator. When the input signal frequency is equal to fc, output voltage should be 0 and it is deviate from its carrier frequency fc. The output voltage should be proportional to the deviation. So it should be a linear function. Okay, it should be a linear function around the fc. If it becomes less than fc, then it should produce a negative output. So look at here, this is my negative output. And if the carrier frequency is greater than fc, if the frequency is greater than fc, then it should produce positive output in proportion to the magnitude of the signal. So you are looking for a characteristics like this. So we need a discriminator whose characteristics is like this, like a linear function around fc, and the constant kd, k suffix d, is nothing but slope of the straight line. Okay, let's say this is 1 and this one is kd. When the input frequency changes by 1 unit, the output voltage changes by k suffix d unit. That's what we mean by when input frequency changes by 1 unit, the output voltage changes by k suffix d volts, because output is in voltage. Or we are generalizing the statement k suffix d units. Here the unit is voltage and here the unit is frequency. Okay, so this is the ideal characteristic of FM discriminator. Okay, so when you are designing a FM discriminator or FM demodulator, then the characteristics should be a straight line. It should be straight line. For example, if you plot the characteristics of a diode in the forward bias, it is its characteristics. Similarly, I have a circuit here. Some circuit I don't know, we need to yet to see that, but its characteristics is a straight line. Okay, therefore when you design an FM demodulator, then you should always keep in mind that it should be a straight line. Okay, right now we are looking at the principle as we were, okay, as what do we need to do in order to demodulate. The question of how to do it still remains. That is something we still need to address. But before we do that, we take up the question of how to realize such a characteristics. Let's consider the situation when the input signal is phase modulated signal. Okay, now if I have a frequency discriminator, one can ask a question that can I use it to demodulate the phase modulation? So that is the question in front of us. It is actually a frequency demodulator, but the input signal is phase modulated signal. Now, can I use this frequency discriminator to demodulate the output? The answer is yes, you can do that, but before that the output is given to output of your discriminator is given to integral of that, and then that is your demodulator output yd of t. Therefore, your y of t is equal to kd times kp times dm of t by dt. So if you remember, how did we realize a phase modulator using a frequency modulator? You first differentiate the input signal and pass that through the FM generator. Therefore, the output of the frequency discriminator is a differentiated version of your message signal. Okay, therefore the FM generator output is proportional to the dm of t by dt. If you want m of t again from the carrier frequency fc, then you have to integrate one more time. Okay, you must integrate the output. Recall the figure from the one of the previous lecture. Like you give m of t, that m of t is first term differentiator and then given to FM modulator, frequency modulator, and that one is phase modulator signal. Therefore, before given to the message signal to the FM demodulator, you are differentiated once. The inverse operation of the differentiator is integrator. Okay, the output y of t in this point is not proportional to m of t, not proportional to m of t, but proportional to what? D over by dt of m of t. Therefore, what do we need to do? We need to integrate. So you must pass it through an integrator, this integrator, to get something which is proportional to what? M of t. That's it. That's what we are doing here. That's it. So that proportionality constant is kd times kp times m of t. That's it. So this is my final output, final demodulator output. So if you have any frequency discriminator, you can use it to demodulate both FM signal as well as phase modulated signals. Okay, so no need to separately develop a demodulator for phase modulated signals. If you have a frequency demodulator, then you can demodulate both the FM signal as well as PM signal. Similarly, by using a frequency modulator, you can get both the frequency modulated signal and phase modulated signal. Now, the question is how to realize the frequency discriminator. Okay, how do we realize it? Okay, so we are looking for some circuit or some systems which can do this job, that is produce an output voltage proportional to the input frequency, proportional to the input frequency deviation from the carrier frequency, because it deviates from the carrier frequency in the forward direction if m of t is positive, and it goes in the negative direction if m of t is less than 0. So this is called my deviation, total deviation. Now I need to get an output which is proportional to the frequency deviation, input frequency deviation around the carrier frequency fc. So there are many ways of doing this. We will consider some of them here. All of them unfortunately will not realize the ideal characteristics. Some will realize ideal characteristics and some may not. Okay, but they will try to approximate this linear curve. The frequency axis, it should be a linear curve like this. It crosses the point, it has a 0 point, and that point the frequency is the carrier frequency, because when the instantaneous frequency is equal to carrier frequency, that times the message signal is 0. Okay, so this ideal characteristics is very difficult to realize them physically. Okay, you will not be able to get them because you will not use some physical device for this, and there is no physical device which will directly do this kind of linear curve, linear characteristics. So you will have to design something and see whether it comes close to the required operations. So let us look at some approximate realizations of discriminator of the ideal characteristics which we discussed till now. So next we are going to talk about approximate realizations of ideal characteristics. One simple approximation can be obtained as follows. Take your received signal, which is x suffix r of t, and pass it through a differentiator. Okay, now you have a system whose output linearly depends on input frequency, right? What is your ideal characteristics? This is f, and the output voltage is linearly depends on the input frequency. If input frequency is 0, the output is 0. If the frequency increases, it gives the positive voltage. If the frequency is negative, it gives the negative voltage. Now you think of ideal differentiator. Let me say d by dt. Okay, what is the frequency response like? You recall from your Fourier transform. You have a signal x of t, take Fourier transform, you will get a x of j omega, right? Now you differentiate the signal d by dt of x of t, then this becomes j omega times, x of j omega. Now if frequency increases, the whole thing will be increased. If this omega decreases, the whole thing will be reduced, right? So you have a system which just carries out differentiation, and it is equal to your j omega. So this property comes from Fourier transform called differentiation in the time domain. So look at here, this j omega is a linear function here. Therefore my output is linearly depends on frequency. So it makes sense that somehow this characteristics, linear characteristics could be realized by using a differentiator. So when you have a differentiator, then somehow you modify that, and then you will achieve this linear characteristics. The only thing is that the differentiator has characteristics not around fc. Suppose if you try to plot this, what will happen? If omega is equal to 0, then this will be 0. When f is equal to 0 or omega equal to 0, 0. When omega is equal to 1, 1 times x of j omega, like that keep on increase. Therefore this characteristics is centered around f equal to 0, but we need a characteristics which is centered around fc. Therefore if you take a differentiator, you can get the linear characteristics like this with certain slope, but centered around where frequency f equals 0, but here it is centered around the carrier frequency. So that is the only difference. Okay, so the differentiator output is centered around the 0 frequency, and the frequency 0, the output is 0. But in your frequency demodulator, what do we want? We want the 0 output at f equals to fc. But differentiator has the characteristics that output is equal to 0 when f equals 0. So that is the only thing we need to address. So there are many ways of doing this. So this is one method. And this is not we are looking for. We are looking for this type of characteristics. Okay, so you have d over dt differentiator. Okay, input is x of t, output is the time domain d by dt of x of t. If you take Fourier transform of x of t, you will get x of j omega. In the transform domain, d by dt of x of t is j omega times x of j omega. So we could call such a device as some kind of a bandpass differentiator. Okay, if you want a response like this, the differentiator is not differentiating the signal at the frequency equals 0, it is differentiating at the point of Fc. Okay, therefore this is called something called a bandpass differentiator. A differentiator which gives you the linear characteristics around some carrier frequency Fc, that is around some center frequency Fc, then you call bandpass differentiator, and that is what we are looking for. So you start with a normal differentiator, just a d by dt operation, and it is not a bandpass differentiator by itself right now. Let's call the output of the differentiator by E naught of t. Let me draw the figure separately. Differentiator, the input signal is the received signal xr of t, and this one is E of t. Okay, so you start with a normal differentiator, just let's say this is d by dt operation. Okay, it is not a bandpass differentiator by itself. Okay, let's call the output is E suffix naught of t. Now pass this output E naught of t through an envelope detector. Okay, what is envelope detector? Envelope detector is a demodulator for AM signals, but here I am going to use this envelope detector for demodulating FM signal. So that is a strange combination, because you can ask me, how can we use an envelope detector which is originally designed for demodulating the AM signal, but here we are using to demodulate the FM signal. Let us see how it works. Okay, so this is a strange combination. You take your FM signal, give it to the differentiator, and then if you pass it to envelope detector, then the output is your message signal, demodulated output Yd of t. We will prove it, no problem. Demodulated output, or you can call detected output, either way. Okay, so this is a typical block diagram representation of your demodulator. Okay, now let's see how this works, or how this can possibly work. Let us try to prove it mathematically. What is your XR of t? Frequency modulated signal that you are receiving. So A suffix c, sometimes I forgot to put this c, doesn't matter. Carrier amplitude A suffix c means cos of omega ct plus phi of t. Now you differentiate this. After this point, what is your E naught of t? E naught of t is equal to d by dt of x suffix r of t. Your cos becomes minus sign, so minus AC, and this argument will be differentiated once. So you will get omega c plus d phi of t by dt multiplied by sine of omega ct plus phi of t. So this is my E naught of t. Now if you see this equation, there are some interesting features it has. Okay, now sorry, if you see this equation, you can observe some interesting features. What are those interesting features? What can you say about the waveform E naught of t? You can think of this as some modulating signal, right? Modulating signal. Let me call some signal, let's say m dash of t or something else. Okay, this guy has some see, this is a constant, by the way, some constant value. some constant values added with the d phi by dt. What is d phi by dt? It is your message signal, modulating signal. Okay, your d phi by dt is message signal. So message signal is added with a constant value, therefore the whole thing I can think in terms of modulating signal. Now the modulating signal is multiplied by whom? A carrier. Okay, therefore this whole combination is something looks like what? Your DSBSC or amplitude modulated signal. In fact, I can say amplitude modulated signal. Therefore omega c times d phi by dt sine of omega ct plus phi of t is something like amplitude modulation of the carrier. In fact, if you expand this, I can write minus AC times omega c times sine omega ct plus phi of t minus AC times minus AC times d phi of t by dt times sine omega ct. Now look at this. This is constant, minus AC omega c is constant. Constant is multiplied by a carrier, but with of course varying carrier. Okay, again this is your FM modulation, FM signal, but with certain carriers. I can say it is carrier. Now what about this? This is again the constant carrier. Here variable carrier. Let's say I can think in terms of variable carrier, and this one is constant carrier multiplied by what? Your message, because your d phi by dt is your message. D phi by dt is a m of t modulating signal. Therefore this whole thing is DSBSC. So if you combine these two guys, then it looks like AM with carrier. Therefore if you differentiate a frequency modulated signal, in some sense you can say that it looks like a AM signal with the carrier. In fact, you can ignore the negative sign, that doesn't matter. Okay, we can always observe this negative sign by putting a plus pi by 2 or minus pi by 2 or whatever here in the argument. It doesn't matter. Okay, therefore the moment you differentiate your frequency modulated signal, it looks like an AM signal. Therefore if it is AM signal, then we know how to demodulate an AM signal. Simply pass it through an envelope detector. That is the reason we put a envelope detector here. Okay, therefore your differentiated signal essentially becomes an amplitude modulated signal. Now you can ask me, is there any difference between the normal amplitude modulation and this differentiated frequency modulation? Yes, there is a difference. Here the carrier is a variable carrier, and here the carrier is a constant carrier. Okay, the carrier also has some phase variation. Okay, nothing is new. But if you look at the envelope, they don't bother us. Okay, for envelope detector doesn't matter whether the frequency is increasing or decreasing, it only captures the envelope of the signal. Okay, for example, you have a signal like this, then you put either a constant frequency like this, or you put a variable frequency like this, very high frequency, then low frequency like this, doesn't matter. The envelope detector bothers only the envelope or trace of the peaks. It least bothers about what happens inside the argument, inside the cosine function. Even if you have like this, then like that, if you took very low frequency also doesn't matter. Even you can put a very high frequency, constant frequency also, it gives the same envelope. So the envelope detector does not depending on the frequency, whether the frequency is a constant frequency or variable frequency or low frequency, high frequency, it always takes care of the amplitude. Okay, therefore the envelope detector doesn't bother the frequency, because you remember the envelope is the trace of the peaks of the carrier. Okay, envelope is the trace of the peaks of the carrier, so the phase variation don't bothers at all. Okay, so phase variation don't bother us at all. So if we produce the output which is proportional to this envelope, where is this? If we produce an output which is proportional to this envelope, then what will I get? I will get a omega c plus d phi by dt. Anyway, omega c is constant, you can remove that. Therefore, I will get d phi by dt. What is d phi by dt? It is your message signal. Therefore, the envelope detector really produces an output proportional to the message signal. So, your FM signal is demodulated by employing a differentiator followed by an envelope detector. Okay, therefore, your y d of t is equal to k suffix d times d phi of t by dt. Okay. That's it. So in principle, by having a differentiator followed by an envelope detector, I can realize approximately what I want. Okay. So let me write down this differentiator output one more time. E naught of t is equal to minus AC times omega c plus d phi of t by dt multiplied by sin omega ct. Now this is like your AM signal. When we say AM signal, then there is one important issue, that is something called a modulation index. That modulation index should be always less than 1. Now if you look at this argument, this part, if you look at this, then this should be always greater than 0, otherwise over modulation occurs. Okay, that means if d phi of t by dt mod of d phi by dt is greater than omega c, then what will happen? Over modulation occurs. Okay, therefore to avoid over modulation, omega c plus d phi of t by dt must be greater than 0 for all t. Therefore the envelope will not be reversed. So this is the condition for avoiding over modulation. Okay, this condition is easily achieved. Why? Your omega c is much greater than d phi of t by dt, because carrier frequency is in terms of megahertz, but after all this is your message signal, right? So it won't affect. Therefore this over modulation is easily avoided in this. So omega c is typically large, so normal condition, so the condition for envelope detector is satisfied. Okay, the magnitude of the thing is the magnitude of d by dt of phi of t must be less than omega c, but anyway this is easily achievable condition. Easily achievable condition. Why? Your omega c is in terms of megahertz, 882 108 megahertz, but here we are talking in terms of message signal, right? M of t may be maximum 15 kilohertz, so it is in 15 kilohertz and this guy is in terms of megahertz, so it doesn't matter. Therefore this condition is always true. But still there is one more difficulty in this. One is the difficulty of realizing the ideal differentiator. Ideal differentiator, that is very difficult to realize. Okay, that is the one that need to be discussed, but it is not still clear how to realize that. Okay, so first condition is realization of ideal differentiator. Mathematically fine, block diagram wise fine, but now we need to think in terms of circuits or devices. Therefore, realization of ideal differentiator is difficult. For that reason, what did we say? We said approximated version of your ideal differentiator. Difficult. So this is one point. And the second difficulty is, the second issue is, what I really want to discuss is that now I will very briefly discuss at this moment. We are ignoring the discussion that the fact the input signal may have some amplitude variations, right? As per the definition of your frequency modulation, it should have constant amplitude. It should have constant amplitude. But what happens in practical life, that once you receive the signal is disturbed by noise. Okay, although at the transmitter, when you send a signal like this, when you generate the signal, there is no amplitude variation at the transmitter, but the channel has noise, which are yet to be discussed, but the noise will add with this guy. Noise. Because of the noise, a constant amplitude FM signal becomes, it will not be constant, sometimes it will go up and come down like this. And this portion occurs, this extra thing, this occurs due to the channel noise. Due to the channel noise and other distortion, the amplitude is not constant in the output. Okay, so that is very important point that we need to consider. So the channel will add noise, and a result of that, the received signal will not only have phase variations or frequency variations, but also have amplitude variations. So the differentiation will be sensitive to both the amplitude variations and phase variations. Okay, so it is also going to depend on amplitude. The fact that input amplitude A is no longer a constant. Previously, what did we say? Your XR of t is equal to a constant, right? Constant times cos of omega ct plus phi of t. Now, because of the channel, your received signal is due to channel. Your received signal is, it is E of t times cos of omega ct plus phi of t. Okay. Therefore, your amplitude is no longer a constant, but it is a time varying thing. So, you have a product of two time varying functions. This is my first time varying function and second time varying function. Now, you need to differentiate this. Apply UV rule, u dash v plus uv dash. So, your differentiator output then is not going to proportional to only this omega ct plus phi of t, because the amplitude variation will also affect what you finally get at the demodulator output. Okay, that's something we need to remark. Therefore, the above system, this system, your differentiator followed by envelope detector is sensitive to amplitude variations as well. The system is very simple and very nice, perfectly no problem, but differentiator followed by followed by envelope detector is sensitive to amplitude variations as well. So if amplitudes are varying, then this is sensitive. But that originally in the frequency modulated signal we did not have any amplitude variation. So this amplitude variation comes because of your channel. So that unnecessarily gives some kind of distortion in your message signal. Therefore that one has to remove. Okay, it is therefore not an ideal discriminator, this one, in that sense. Not an ideal discriminator. Why is it not an ideal discriminator? Because of the variation in the amplitude. So to make it behave like an ideal discriminator, what do you need to do? You make it constant amplitude. Okay, so the only solution, only remedy is, whenever your amplitude is changing, in your amplitude modulated signal, it is changing, what you do? You remove these guys. Okay, these guys you remove it. Whenever it crosses, you remove that. So you have to make sure that the input FM signal that you present to the frequency discriminator, it must have a constant amplitude. So we need to ensure that the input angle modulated signal is of constant amplitude. So if it is not of constant amplitude, we will have an output yd of t, which will have dependence on not only dphi by dt, but also the time varying a. That's why I put uv dash, u dash v plus uv dash. Originally my d by dt, I mean your y of t, yd of t is proportional to d phi of t by dt. Now if the input is frequency modulated signal is changing in amplitude also, then it is going to be proportional to d phi of t by dt plus some a of t also. Okay, so this comes from the variations of the amplitude. Okay, input signal amplitude varies, then those variations will also produce an output. So there will be proportionality because of this a of t guy. Okay, therefore there will be a component because of this a of t. So this requirement can be met by a device called a limiter. So how can we remove this guy? There is some device called a limiter. So more precisely it is called a band pass filter. Let us see how the band pass filter, I mean it's not band pass filter, band pass limiter. I'm sorry, band pass limiter. Now let us see how the band pass limiter looks like. You have the received signal xr of t, you give it to amplitude limiter. Okay, so this amplitude limiter has input output characteristics which looks like this, some positive value and negative value. This is my Vi and this is my V naught. So let's say this is Vi and V naught, right? The moment the input is positive, the output is saturated to a fixed value. Okay, let's say Vi is the instantaneous input voltage. And V naught instantaneous output voltage. Any moment, if the input amplitude is positive, the output is a fixed value. Okay, let's say this value is some fixed value, let's say plus 1. Okay, and if the input is negative, then the output is fixed to minus 1 volt. Okay, you have FM signal coming in here. coming in here which has some amplitude variations. Okay, so this is my input FM signal, but this FM signal has some variations. What will be the output of this amplitude limiter according to the characteristics? Okay, the input is a sinusoidal wave. The moment it crosses towards the positive side, what will the device produce? It produces the positive value, let's say plus 1 volt. Okay, it will produce a constant amplitude. Constant amplitude. From there onwards, as long as it remains positive, your input is positive. Like this, as long as the input is positive, it stays at plus 1 volt. The moment you go to the next half cycle, it will be minus 1 volt. Again, if you go back to positive half cycle, it is plus 1 volt, minus 1 volt, plus 1 volt, minus 1 volt. Like that, it produces a square wave. Therefore, the entire positive half cycle would become a constant value equal to plus 1. Similarly, for the entire negative half cycle, it will become a constant value which is equal to minus 1 according to the characteristics of your amplitude limiter. So, what kind of operation are we performing here? This is something called a hard limiting operation. Okay, hard limiting operation, because you are basically converting a smooth sinusoidal signal into a square wave kind of frequency modulated signal. Let's say your signal is like this. Like this, then like this. Let's say this is my typical amplitude modulated signal. There is some positive peak due to noise, and then there is like this, like this, like this, like this. These are all noise component like that. Okay, here also some noise component is sitting, and here also some noise component is sitting. This is some noise like that. Now, output of your amplitude limiter will be all are very closely spaced, some lines and all. Like this. Let me enlarge this. Now, during the positive half cycle, it produces plus 1 volt. That's what we said, right? So the entire positive half cycle, the output will be a constant value which is equal to plus 1. Let's say this is my plus 1 volt. It is constant for entire positive half cycle. For the negative half cycle, it is minus 1. And then it is plus 1, minus 1, plus 1, like this. Like that it keep on goes. Okay, so we are basically converting a smooth sinusoidal signal into a square wave kind of frequency modulated signal. Again, here also see the period is not same. Okay, here it is highly compressed and here it is sparsely located. So instead of modulating your message signal by a sinusoidal carrier, you are modulating the message signal by a square wave carrier. Okay, the input waveform, let's say like that, like this, due to noise. This is my input waveform, Vi to the modulator, and this one will be V0. Okay, during this positive half cycle, from this to this positive half cycle, it will produce plus 1 output. During the negative half cycle, in this duration, it produces negative -1 output, and so on and so forth. This limiter is also called a hard limiting because it converts smooth variations into just hard +1 and -1 variations. As you can see, the frequency variations will be captured still by 0 crossings of the square wave. This 0 crossing point, this 0, this 0, all are the same point. The 0 crossing points are not changed. It is not exactly a pure square wave. It is a modulated square wave. It is a modulated square wave. Okay, but this is not what we want. We want a pure frequency modulated signal. Okay, the way you had written in the written mathematically a few minutes ago. To do that, what you have to do is pass this square signal, modulated square wave to a band pass filter centered at Fc. Therefore, the band pass filter will convert this modulated square wave into modulated sinusoidal signal. Okay, so you just pass it through a band pass filter with a center frequency Fc, and this combination is called a band pass limiter. Like you have limiter, amplitude limiter, and the output of the limiter is a square wave like this, and this one is given to band pass filter centered at Fc, and this is your XR of t. Now this whole combination is called a band pass limiter. So mathematically this will produce an output in this point, an output here, finally a pure FM signal. Exactly constant amplitude, it varies like this, like that, but it is a square wave, and here it is affected by noise, like this noise signal. So these noise portions are removed, they are noise. So the output of the limiter is a square wave, and the square wave is connected to a pure sine wave, pure FM signal by the band pass filter. So the amplitude variations are killed by this limiter, amplitude limiter. Okay, you can look at here this see, this cycle has large amplitude, and here also I have large amplitude, and here also I have large amplitude. These large amplitudes are removed by the limiter. Maybe look at here, this has smaller amplitude. So whether it has a larger amplitude or smaller amplitude doesn't matter, it produces a constant amplitude frequency modulated signal, and this all are disappearing once you have the hard limiting operation. That was the reason we put the limiter. However, to convert back into the sine that we started with, we must pass it through a band pass filter of center frequency Fc with a sufficient component, so that all frequency modulated components pass through. So let me take the mathematical analysis of this band pass limiter. Okay, but I think the purpose of keeping it here is clear now. If you don't have a limiter, then we will be in trouble. Killing the amplitude variations first through the limiter, and then converting back into the FM signal with a sinusoid carrier by using a band pass filter. That is the basic purpose. And clearly this limiter is a non-linear device. Very clearly you can see. Why is it non-linear device? Yeah. Non-linear device, because the output input output characteristics is like this. Okay, this curve is obviously not a linear function, it is a non-linear function. Okay, limiter has highly non-linear input and output characteristics. So this whole entire thing is a non-linear system. Okay, so your limiter and bandpass filter together is a highly non-linear system. Okay, now we are ready to use our combination which we just discussed. So limiter, the output of the limiter is given to bandpass filter with a frequency Fc, and this is received FM signal, and this one is given to your differentiator d by dt, and this is given to your ED, envelope detector. And the thing is, we are assuming this is ideal differentiator. Okay, so the system comes pretty close to being an ideal frequency discriminator. Okay, why do we need this combination? Because in the received signal, let's say XR dash of t is not constant times cosine signal, it is some time varying function E of times E of t times cos of omega ct plus phi of t. But ideally we want how your received signal should be, XR of t should be A times cos of omega ct plus phi of t. This is ideal, but this is practical in practice. Okay, in practice you will get the signal like this. Okay, the function of the limiter and bandpass filter is the combination of limiter followed by a bandpass filter, okay, which we are calling bandpass limiter. If your input signal is not of constant amplitude like this, but has some amplitude variations, that is A of t, function of time, which we know is an undesirable thing as far as operation of this your differentiator and the envelope detector. Okay, therefore we need to remove this A of t to A, because if you feed this A of t to the differentiator directly, the output at this point, let me say this point, will not be proportional to only d phi by dt. It will also have some additional dependence on the A of t, okay, because A of t is a time function, and that we don't want. Therefore this A of t is we don't want. Okay, A of t we don't want, what we want is A only. So what we need to do is convert to our good old XR of t, which is A times cos of omega ct. Okay, so this A of t have to convert into A times. So that is our object. So for that reason only we are using this bandpass limiter followed by bandpass filter. Okay, this one is pure angle modulated signal. The second one is pure angle modulated signal. And what about the first one? This one is the pure angle modulated signal but disturbed by noise. So precisely how do we get this a signal which is affected by noise to a purely angle modulated signal? By using this bandpass limiter. Okay. Therefore, my objective is to kill the amplitude variations. I have to somehow remove this amplitude variation. I don't want A of t. So somehow convert this A of t into a constant A. So the objective of your limiter and bandpass filter is how to convert a non-constant amplitude angle modulated signal into a constant amplitude angle modulated signal, so that we can feed it through the differentiator and the envelope detector to produce the demodulated signal. Now one can ask a question, how this bandpass filter is producing a pure sine wave when the input is a square wave. Okay, some people think that output also is square wave. If the input is a square wave, then output also square wave. No, it cannot be. Okay, you take any filter will not give square wave because it has abrupt transitions. If you give a square wave like this, then the bandpass filter will give a pure sine wave. Okay, intuitively bandpass filter is a resonant circuit. If you recall, it has RLC component, okay, tuned to a specific frequency with a certain bandwidth. So you cannot produce a square wave here at the output term. Okay, it cannot produce a square wave. So recall from your filter theory. Okay, you cannot produce a square wave when the input is like a square wave or something else. It will only pass the components around the center frequency of your bandpass filter. Okay, so that's it about your frequency discriminator. Okay, in the next lecture we will talk about a realization of your differentiator, how we can realize the differentiator. Okay, what are the different ways which are available to realize the differentiator. Okay, so that's it about the frequency discriminator, frequency demodulator. So let me stop at this point. Thank you very much.